Okay, intermolecular forces in action. We talked about the different types of intermolecular forces. Now we're going to see some effects of those intermolecular forces. Of course, the most important one is probably the very existence of solids and liquids. Without intermolecular forces, we wouldn't even have solids and liquids. But other properties that are significant include surface tension, viscosity, and capillary action. Here we have a picture of a paperclip floating on water. Have you ever done that? It's kind of cool because it shouldn't be able to happen, right? Paperclips sink in water. So do needles. You can float a needle on the surface of water. You can try that at home. Just make sure that the container is very, very clean, no soap residue, and that the water's clean and your fingers are clean and the paperclip's clean, and you do it very carefully. Same thing happens with the little water skaters on the river or on the pond. They skate along on top of the surface of the water, which seems impossible. This is due to surface tension. And the way they photographed this with the reflections here, we can see this very clearly, that it almost looks like there's like a pool cover or something over the surface of the water, like a skin on the water that the paperclip is on, and as it pushes down, it's depressing that cover, right? That's kind of what it looks like to me. It's actually the surface tension, the water not wanting to separate and let the paperclip in. So we can define surface tension as the tendency of liquids to minimize their surface area. It can be measured with numbers. The unit is millijoules per square meter. So we quantify it as the energy required to increase the surface area by a particular amount. So for water, the surface tension is 72.8 millijoules per square meter. To increase the surface area of water by 1 square meter, it would require 72.8 millijoules of energy. That is not a number that you need to memorize, but I just want you to be aware that, yes, there are units and ways of quantifying this. So here we have another picture showing us surface tension. Here's a trout fly. And again, you can see sort of where the water is pressed down, but the fly isn't able to penetrate it. It just floats on top of it. Not like a cork floats, where it's actually in the water. This isn't floating because it's less dense. It's sitting on top of the water. It's not able to penetrate the water. So how does that work? Here we have a two-dimensional illustration of water molecules. So of course it's three-dimensional, but that's too confusing to draw. So if we look at a water molecule down in the interior part of this sample of water, it is attracted to neighboring molecules. Here we're seeing six neighboring molecules that it's attracted to. And of course that attraction would extend in 3 dimensions as well. This molecule at the surface is attracted to a neighbor on each side and 2 on the interior, but it's only interacting with 4 neighbors. So the water molecules are attracted to each other. Do you remember which intermolecular forces water has? That has hydrogen bonds. That's the strongest one. What else does it have? It's polar, so it has dipole-dipole forces. And what's the one that everything has? Starts with a D. Dispersion forces. Everything has dispersion forces. So water's got a lot of forces of attraction holding it together. Well, the more attraction, the more stable it is, the lower the energy. So this molecule in here, being attracted to all of its neighbors, is lower in energy. This molecule has higher potential energy because it has less attraction to its neighbors. So the molecules at the surface have higher potential energy. The ones in the interior have lower potential energy. Lower potential energy is more stable. In order for something to penetrate this surface, we're going to have to push these particles apart and increase the surface area so that there's a place where this object can get into the water, right? We have to disturb these interactions, and that requires energy. So the water wants to minimize its surface area because the surface molecules are those with the higher potential energy. It wants to have the lowest potential energy, which means more molecules on the inside, fewer molecules on the outside. So there's different ways to think about this. In order to penetrate the water, you have to push molecules apart, and the water doesn't like that. They're attracted to each other. It's like trying to push into a group of people that are having a great time. They don't want to be separated, right? Any questions? We see that surface tension decreases if the intermolecular forces decrease. So weak intermolecular forces lower surface tension. So here's this picture again from the first slide. Do you remember that video with the wringing out of the water? So here's the astronaut, and he's got this giant drop of water just hanging in front of his face. I love how they centered it so that you can see his inverted face inside the drop. It's kind of neat photography there. Water forms spherical drops because that's the shape that has the smallest surface area to volume ratio. In that shape, we get the smallest surface area. Small surface area means lower potential energy. And so what happens here is if there's a whole bunch of little droplets, more droplets is more surface area, and so if they are able to touch each other, they will combine into one giant drop because that will minimize the surface area. We don't see giant drops like this on Earth because of gravity. Here there's no gravity pulling on this. On this spider web, we see these little tiny droplets. They're all pretty much spherical to minimize the surface tension, minimize the energy. And they won't get any larger because when they get larger, they fall off due to gravity. Usually when we draw a water droplet, like let's say we have a dripping faucet, so annoying, right? Dripping faucet, you'll see a water droplet and it kind of has this teardrop shape, right? Well, the teardrop shape is due to gravity pulling on the droplet of water. We see that at the end of a burette, too. You can open the burette stopcock just a teeny tiny bit, and you can see this water droplet grow, right? When it gets to a certain size, it's going to fall. The size of that drop has a lot to do with gravity, and it also has something to do with the specific material that the droplet is hanging off of, how strongly the water is attracted to that. And this is one of the things that gives away some of those movie-making techniques where they use miniatures, because it's really difficult to make miniature water droplets. And so you look at those and your eye says, this doesn't look quite right, but you can't really put your finger on what's wrong. A lot of times it's the water. The droplets are far too large, and we can tell that relative to the little boat or something. It's like, wait, something's off, because our eyes recognize how water normally behaves. So larger drops like this get distorted by gravity. Any questions? Another thing is viscosity. Where I've heard this word the most often in just regular life is commercials for motor oil. They talk about viscosity breakdown and how this is a bad thing, right? The viscosity of your motor oil is important. Viscosity is the resistance of a liquid to flow. So we think of a more viscous liquid as being like thick, right? So can anybody think of a thick liquid? Pardon me? Oil, yeah. How about something in the kitchen that you might eat? Syrup or honey. Syrup and honey and motor oil are more viscous than water. Especially when your honey is cold, man, you just like waiting forever. You can see it moving, but it's like, come on out of that stupid bottle, right? It just will not come out. It's moving so slowly because it's very viscous. Viscosity can also be measured. The unit for that is a poise, which is kind of a funny unit, but it's a capital P. It's 1 gram per centimeter second. It's just there so that you've heard of it. We're not going to actually use it. Viscosity is greater in substances that have stronger intermolecular forces. In order for a liquid to flow, the particles need to slide past each other. If they're sticky to each other, if the forces attracting them are strong, then it's harder for them to move past each other, and the flow is going to be slower. Does that make sense? So it's like people wearing Teflon suits versus people wearing Velcro suits and milling about in a very crowded space. If everyone's wearing slippery clothing, you can just slide through people, right? But if everyone's got Velcro on, you're going to kind of stick, and it's going to be harder to get through, and so the movement will be slower. Viscosity also has a strong dependence on molecular shape. We said earlier that molecular shape affects the dispersion forces. So in this table, we're comparing some alkanes, pentane up to nonane, and these are all the straight chain alkanes. So here are their structural formulas. They're just long carbon chains. They're all carbon and hydrogen bonds, and so these are completely nonpolar molecules. We see that the molar mass increases. Increasing molar mass gives you increasing strength of dispersion forces, and these increase also because their surface area is getting longer and longer. And so these are like, I can't point to the bottom one. So we'll point to octane, which is the lowest one I can point to. Octane would be like a longer strip of Velcro than pentane, a shorter strip of Velcro. Less surface area for the pentane means it's easier to pull it apart, and so it's less viscous. And here the viscosity is quantified, and we see that the viscosity does increase as the length of those molecules and their molecular mass increases. Any questions? Viscosity depends on temperature. Temperature is the average thermal kinetic energy of the particles. So at a high temperature, the particles are moving more, right? And so at a high temperature, they are more able to break those, or partially break those intermolecular forces that are holding them together and resisting the flow. So at a high temperature, the liquid will flow more easily because the viscosity goes down. What happens if you heat up the pancake syrup or you heat up the honey? It flows more easily, right? Because the viscosity is lower at a higher temperature. So this, is pretty important in your engine because you run your engine and it gets hot, right? But when you first start your engine, it's cold. Motor oil needs to coat the moving parts in your engine to lubricate them so they don't rub on each other. When the oil is very cold, it can get too thick, too viscous, and then it will actually impede the movement of the parts instead of aiding it. When the temperature gets high, the oil could become too inviscid, not viscous enough, so that it's not sticky enough to stay up on the parts. It's more liquidy like water, and it'll just run to the bottom and sit in the oil pan and not do any good. So that's why the viscosity of motor oil is important. It needs to be just right for the conditions in which you're operating. Modern motor oils are really awesome. They use polymers, and so what these polymers do is they coil up at low temperatures and unwind at higher temperatures. So how does this work? Well, so we've got them coiled up at low temperatures. Two spherical things can only contact each other over a very small surface area. And so they're only able to stick together a little bit. At low temperatures, where the movement of the particles is less, this helps to lower the viscosity when it's higher due to the low temperature. At high temperatures, the polymers uncoil and straighten out, and this increases their surface area. At high temperatures, viscosity is lower, and this helps to moderate the viscosity. So these modern polymers allow the oil to be appropriately viscous over a wide temperature range. I think that's pretty cool. Here's also a table just showing liquid water, the viscosity at several temperatures. At room temperature, the viscosity is 1 centipoise, and as you increase the temperature, it goes down to 0.282 at the boiling point of water. You probably don't notice the change in viscosity of water as it heats up because it's not very viscous to start with. So the change is not that obvious. But you do notice it with something like honey or pancake syrup. And most of us don't play around heating motor oil in the oven or in the microwave. I wouldn't recommend it. So we don't necessarily notice that either. Any questions about viscosity? Capillary action. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. So here someone's getting some blood drawn, and I get this little tube here, and you touch it to the blood, and the blood just runs up the tube. Have you ever had that done? I usually choose not to watch because I just feel better if I don't watch them do that. But it's fun to watch someone else have that done. How does that work? That's defying gravity, right? That shouldn't happen. Well, there's two different forces going on here. There's cohesive forces and there's adhesive forces. So cohesive forces, that's the intermolecular attractions between the molecules in the liquid, between the different molecules that compose the blood, which, there's a lot of water in blood. So that's what holds it together as a liquid. Adhesive forces are the attraction between the liquid and the surface of the tube. So if you notice here on this big one, you can kind of see that meniscus, right? And we've seen that in our burettes and in our graduated cylinders, this curve in the surface of the liquid. Why does it curve up on the sides? It's the adhesive forces. So the water, the liquid, is attracted to the glass surface. And so it begins to creep up the side of the tube. And it's pulling its neighbors behind it because they don't want to lose those attractions. But it's not going to go on indefinitely because gravity is also pushing down. In a wide tube, it creeps up a little bit. The narrower the tube, the higher it goes. Here it's way up here. So very narrow tube, the liquid will just rise up all by itself. So it's a function of the strength of the intermolecular forces, the diameter of the tube, and of course the strength of gravity pulling down. Questions about that? Here we have a test tube with water and a test tube with liquid mercury. Here's our familiar meniscus, kind of looks like a contact lens sitting on the surface there. It goes up at the corner, at the edges, because there's no corners in a round thing. It goes up at the edges because of those adhesive forces. In mercury, the meniscus goes in the opposite direction. It bulges up in the middle and it's down at the sides. Is mercury attracted to glass? No, it isn't. Its adhesive forces are much weaker than its cohesive forces. So it's bulging up in the middle because it would prefer to just be a sphere and minimize the surface tension, minimize the potential energy by minimizing the surface area. So it's trying to be a sphere. So the meniscus is a different shape. You can also look at the meniscus for water and see that depending on the material of the tube, the meniscus can have a different amount of curvature. In some plastic graduated cylinders, there's really almost no meniscus because the plastic is not attractive to the water, and so it's more of a flat surface. But glass does have attraction for water. Questions?